Hello, my name is Vicente Matellan. I'm from CARLA, and I'm going to present you the work titled Using HPC as a Competitive Advantage in an International Robotic Challenge. This work has also been co-authored by researchers from another two institutions. First one is the Grupo de Robótica from Universidad de León, and the third one is the Intelligent Robotics Lab from the University Rey Juan Carlos, the three of us from Spain. The outline of this presentation will follow the next four topics. First, I'm going to give you some context, in particular related to the robotics competition and the CyRock European competition in particular. Then I'll present you GentleBot, the joint team by the University of Juan Carlos and University of León that entered that competition, and the facilities of the Centro de Supercomputación of Castilla y León, SCAILE, has been supporting these activities. Then I will focus on the software use during the competition, in particular the robotic framework BICA for implementing the robotic part. And then we will focus on the object recognition software use was YOLO. Then I will show you the different alternatives for the training of the neural networks used in YOLO. I will give you some dimensionality of the two alternatives or used during the competition, the tests that were performed, and some discussion about it. And I will finally present some conclusions and further work. So I'm afraid that most of you don't know anything about robotic competitions. There are some of them very popular, as the RoboCup, which is a international competition focused on robotic soccer. The success of these competitions has led to many regional ones, as this Smart City Robotic Challenge, CyRock, that is a European project. This competition is a biennial international competition that was held last year in Milton Keynes in the UK. And the idea behind these competitions is to be able to obtain replicable results and also to have some consistent benchmarking among different approaches to robotic problems. In particular, CyRock is organized in what is called episodes, and GentleBot's team entered two of these episodes. Episode 3, it is named Deliver Coffee Shop Orders Scenario, where basically the robot has to go around the tables of a coffee shop, take the orders for the clients, go to the bartender and check that the orders has been correctly delivered, and going back to the clients if this has not been the case. And episode 4, it's take the elevator scenario, where the robot has to wait for an elevator, enter in the elevator with another people, obviously managing the human-robot interaction, and then ask for the humans to mark the floor it wants to go, and be sure that it's leaving the elevator in the right floor. Just to give you some ideas, I want to present you with a couple of videos of this. Now, scenario 3. The idea is a robot serving in a coffee shop. So the robot has to go to the different tables at the restaurant, check with the clients what they want to order, and also check if the tables are empty or there are different objects on the table in order to clean the table or to order the bartender to clean the table. The robot has to go to each of the tables, ask the customers at that table what they want, and take that order. The robot has to check with the clients that the order that they have made has been correctly understood. Clients usually make their commands verbally, but they can also use the touchable screen in the robot. Once the orders have been captured or recorded, the robot has to report it back to the bartender and repeat the orders. And then the bartender will put the different orders for the robot, and the robot has to check that they have been correctly understood by the bartender. If some of the objects is and correctly understood, he has to ask the bartender to remove it. And then finally, the robot has to deliver each of the orders to the table where this thing has been done. The trial is not for manipulating, it's just for navigation. In the videos, you have seen some of the members of the team, but here you can see the whole Gentlebots team that entered the Milton Keynes competition last year. This team, it's a joint effort between the University of León and University Rey Juan Carlos in Madrid, and they use the same robot. It's a Tiago robot manufactured by PAL Robotics. The third institution involved in this work, as I previously mentioned, it's SKYLE. SKYLE is the Centro de Supercomputación de Castilla y León. It is a regional supercomputing facility established in 2009, and it's part of the Spanish National Supercomputing Network, led by the National Center in Barcelona. And it has been keep growing since creation in 2009, when we started with 29 teraflops. Currently, we are over 400 teraflops. This gives you more or less the context of this work. Focusing on the work, the software that has been used can be divided into two parts. One is the robotic software that can also be divided into two parts. One is the use of the standard robotic operating system, ROS, which was used to interact with the robot. And over this operating system, this framework, we created our own cognitive architecture that is named VICA, where the high-level behaviors can be defined. But for the sake of this work, the most important part is the software used for object recognition. In particular, in episode 3, in the coffee shop orders, we have to recognize different types of objects that are on the tables, both in the client tables and also in the bartender table, as shown in the videos. For this purpose, we have used YOLO. You only look once software, and in particular version 3, which has an underlying deep network named Darknet. And in particular, we use Darknet 53, which means that it has 53 deep levels, which is the process that YOLO, or we have to use to train YOLO for this particular task. Well, we take the objects, and this is one of the problems in the competitions. The objects used during the competition are only available at the beginning of the competition. When the team arrives in Milton Keynes, they don't know which real objects will be used. You have some pictures on the left about the objects. So what we have to do is to recording videos of these different objects and then manually label these objects. As you can see in the middle image, we have to draw manually a box around these objects in order to build a test bed for training. And then once this training has been made, YOLO is able to recognize different objects and people in the images. To give you some dimensionality about this process, we take more or less 2,000 of videos, short videos, less than a minute each. And from these videos, we extracted some images. From these images, we made some transformations to obtain different or more large number of images. In particular, we make horizontal and vertical flips, we made rotations, and we also made some automatic changes in brightness, intensity, of contrasts, up to almost 500,000 images. So from a few minutes of video, we obtain a data set of almost 500,000 images. We divided this data set into two parts, as is usually made in this field. 80% of the images more or less were used for the training and 20% for the validation. And during the experiments, we tried to compare if it was possible to train locally the network using an i7 regular server, and also comparing with the facilities of the supercomputing center as Sky. The idea of these experiments and also the aim of the paper was to test the different values of the YOLO parameters for managing the pipeline of the training. Um, Basically, there are two parameters that we will testing, and was the batch size, which is the number of images processed in each iteration, and also the number of subdivisions, which are the number of mini batches used to train YOLO. Uh, the subdivisions must be a divisor of the batch size because each mini bytes is processed by each of the GPUs during the training. So the smaller the number of the mini batches, the more GPU resources will be needed, and also the faster of the training will be. But also the modification of these three parameters has repercussions on the performance of the training. We will be evaluating this performance using basically two parameters, two metrics. One will be the time and the other one will be the loss. Basically, time describes or summarizes the time duration of the neural network training, while the loss represents the error made at the end of each of the iterations. The tests that we have performed are summarized in table one. Basically, we have been running tests of 3,800 iterations due to the fact that the training on the personal computer took too much time. I mean, only 3,900 iterations means that we will be using only 91 and 200 images if you multiply the number of iterations by the batch size. The batch size, as I previously explained, defines the number of samples that will be propagated through the network, which means that, for example, for a set of 20 images in a batch size of 10, the first 10 images will be processed in an iteration, and the next 10 will be processed in the following iteration. In our case, the batch size chosen for all the tests was the same and was 24. And in the case of the test that will be running in Skyle, we use subdivisions of 12, 8, and 4. The second table in this slide basically summarize the results obtained from carry out the YOLO training with the parameters described in table 1. For this training, the total training time is shown, and also the minimum and maximum time per iteration is precise. Regarding the criteria to compare these environments, this figure summarizes or shows the training time values. The blue line, the line on the top, is the time used by the personal computer, and the other three lines show the time used using the different configurations in Scala. Obviously, the time in Scala is lower, and also is lower if you are using smaller subdivisions. But this is one of the parameters. The other one was the loss that is shown in this figure. As you can see, we are using the same colors. Blue is for the personal computer, and the other three are the different configurations used in Skyle. But as you can see, in spite of starting with different loss, all the tests tends to have the same loss at the end. But it's important to remark that this loss is achieved in a different extent of time. To better show this, this figure shows that the test carried out in the personal computer needs more time to get the same loss that the test performed in Skyle. You have to take into account that that the team, the Gentlebots team in this type of competitions plays against time. For instance, in SciRock competitions, these are only assigned a 2 hours slot in the setup date, and in this slot, the team is the only moment we can access the real scenario to record the video, that I mentioned previously, and this is the time that has to be used to label the images and to upload it to the cluster. All those modifications that I mentioned previously made to the images were made in the cluster, which saves a lot of time. So, to finish this presentation, just some conclusions and some ideas about the further work. Basically, in this paper, we have described the comparative study for training an artificial neural network in an HP facility versus the same training in a local computer, also in an environment where time restrictions are significant as an international competition as a cyborg. In this environment, in a competition, hard real time is not really required, but deadlines, a few hours in our case, as we have previously explained, are firm. So we try different configurations of the workloads, uh, obtaining as a result that the use of a supercomputing facility in this type of competition is not only feasible, but also that let the team reduce the training time of the neural network using YOLO by more than 70%. And furthermore, the use of CARLA has also let the team discover that by reducing the value of the variable subdivisions, we can reduce up almost 15 or even 20% plus the time of training using this type of facilities. Also, about the further work from the point of view of the team, we will really will be using CARLA to carry out the training of the neural networks, but probably using a different object recognition software. And also one of the concerns is how to reduce the image tagging time. And from the point of view of CARLA, the question is how to packetize this type of service. I mean, we are used to deal with workloads that are in our system for weeks, and we have a queue that we are used to manage. But this type of research that requires real-time deadlines is something new that we have to deal with. That's all. Thank you very much for your attention, and I will be very happy to answer you any questions for my email or another method. Thank you very much.